All right, hey, how's it going, guys? Are you ready to go? I am definitely ready to go because today we got the final theorem of the chapter, chapter 5, similar polygons, proportionality. So let's go. We're looking at a diagram right here. We're going to work with this one. We're going to get a third way to look at things that get divided proportionally today in section 5-6. And here we got a triangle, right? We start with this triangle DEF. There are three triangles in this diagram. That's a little bit confusing, but we have a triangle that is the triangle of interest in this one, triangle DEF, and it looks like we have an angle bisector. The triangle angle bisector theorem coming your way in just 1 second. All right, so let's move on over to this theorem here, the triangle angle bisector theorem. Start to figure out what this is all about here. Here's your if statement. Okay, so start writing down this theorem. Definitely put it in your notes here. You have to keep track of this one. I always kind of forgot about this one. I was learning the first time I didn't hear. So anyways, if you start with a triangle, right, and here we have triangle DEF, if a ray bisects an angle of that triangle, and what do we know about angles, okay? What do we know about angles? Well, any angle is going to have an angle bisector. So this proof that we'll prove this in a second, we're going to prove using this angle bisector right here, so a ray DG, but of course this would have an angle bisector here, this would have an angle bisector here, okay? So what we'll prove in a second goes for any angle bisector of any angle of a triangle. But anyways, if a ray is that angle bisector of a triangle, what do you think it is that we can deduce from there, okay? We're in section 5-6, where our theorems have been about dividing proportionally. So maybe let's look at this here. Maybe hypothesize. Well, could this possibly be? This ray is bisecting this, right? Angle 1 is congruent to angle 2. Okay, that's sort of your definition of angle bisector. Well, how might this be divided proportionally? What does that mean? Well, maybe we should actually look at this, perhaps sketching it out real quick here, and maybe we can talk about where we might see proportionality on this one, right? So let's take a look at it for a second. So I might draw a triangle a little bit differently than what you're saying. Let's do maybe triangle ABC, perhaps. Not quite a right angle, a little cute up there, but it doesn't really matter. Just a generic kind of scaling triangle right here. Okay, yeah, it's probably scaling. This is probably longer than this here. It's probably not isosceles. But anyways, let's say here angle A gets bisected. Okay, I'm going to kind of estimate this, just a sketch. Put this in your notebooks, right? Put this in your notebooks. We can work off of this one here. If a ray bisects an angle of a triangle, again, I have an angle bisector here, but the protractor posture would say there's exactly one that bisects angle C, bisects angle B, right? But I want to maybe look at angle A here, just so we can all work off of one angle, okay? So I'm going to sort of estimate. I'm not going to do that little constructions thing you've seen in some videos here, with a little compass and my straight edge tool. So I could show this, right, very, very precisely, but this is just a sketch you should put in your notebooks, okay? So I'm going to kind of estimate. That looks like probably a pair of, like, I don't know, 30-degree angles. And there we go. We got ourselves an angle bisector here, right? That ray, okay, ray AZ is the angle bisector of angle A. So I'll maybe mark it up as such here. Check it out here. How might you think we see proportionality kind of shown here? What are your observations, okay? Let me pause for a second. What are your observations? How might something have gotten divided proportionally? Because remember, we've had two theorems so far about things getting divided proportionally, right? The basic proportionality theorem, right? When we have a line parallel to a third line of a triangle, it's going to, and it intersects the other two sides, it's going to divide those two sides proportionally. Corollary of that, when we have three parallel lines and they're cutting two transversals, those two transversals get divided proportionally. So the question is, what does this ray divide proportionally, and how? And how? What might make sense based on the way you're looking at this one here? Well, I might change colors for a second. And in case you didn't hypothesize this, because we're not in a class right now, you don't have a chance for somebody to throw this one out here. I want you to notice here that BZ, okay, BZ right here. So this ray, okay, will segment out two portions of this larger segment here. And here, notice here, your small segment is this one, and your large segment is this one. Is that particularly significant by itself? No, but you know, an angle bisector is unlikely to go through the midpoint, right? Unlikely to be a perpendicular bisector, for instance, or a bisector of the side here. So this is small and that's large. And what do we notice about the small? It's adjacent to the smaller leg, or not smaller leg, smaller side of the angle that got bisected. Here, this large, right, the large segment that got cut off by the angle bisector here, it's adjacent to the large side of angle BAC, which was the angle that got sort of bisected here. So I might redraw this a little bit here, but here, this small to small, large to large would be actually be in the same ratio. We're going to prove that in a second. They'd be in proportion here. Also, small to large is going to be in the same ratio as this small to large thing here. So that's sort of the kinds of things that we'll prove in a second. We'll kind of see. Okay, so here's the full theorem here, right? If the ray bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides. Okay, divides the opposite side into segments proportional to the other two sides. Let's maybe clear out this diagram here because maybe we want to kind of maybe set a proportion with one another based on what we had here. Okay, quick sketch. We're in blue right now. That was a mistake. I meant to do this in red. But here we had triangle ABC, right? B was over here. Oops. C is right here. Okay, C. And then we had an angle bisector. I'll estimate that's about here. Okay, there is BZ. The one and only ray that would bisect angle BAC. Okay, so this here is my diagram. And just so we can visualize this ray AZ divides, okay, what does it say here? It divides the opposite side into segments proportional to the other two sides here. Proportional to the two sides here. So let me change colors one more time. And we can talk about how we can literally come up with an equation here, right? A proportion that sort of describes what our theorem is telling us right now. We'll prove this one in a second too. We're not just going to accept this one because the theorem will prove it. But here it says here that ray divides the opposite side into segments that will be proportional to the other two sides here. So that sort of tells you how we can set up a valid, a perfectly acceptable proportions here. A ratio over here, ratio over here. So here, divides the opposite side. So that means the ratio of, I'll call this A here, I'll call this B, we'll call this distance C, and we'll call this distance D, right? Sound fair? Those are the four we need to talk about here. If a ray bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides. So the other two sides here, right? This ray that comes down here, the other two sides are in a C to D ratio, okay? So unless this is an isosceles triangle and those two sides would be congruent, right? This is the smaller side, that's the larger side. So let's just say that this would be in a C to D ratio. If this is length C, that's length D. And it just turns out, and this is kind of neat, right? Kind of a neat connection that people discovered, and they proved, the proof is very clever, we'll go through that in a second here, that the angle bisector itself, A and B, going to be in proportion with that. It's going to be the same ratio. Here. So if C is, let's say, 8 and D is 12 and A is 2, then D would be 3, right? D would be 3, for instance. That wouldn't make sense at all, actually. So if A is 4, then B is 6, right? That would make more sense. This would be in a 2 to 3 ratio. Okay? What I could also say with this one here, notice this here, you're going to see this sort of represented other ways as well, too. This is sort of the literal type thing here. Opposite side, that part over that part equals the ratio of the other two sides of the triangle when we have that angle bisector introduced here. But here's the other ways that you might see this, okay? What if I do a mean swap down here? What if I do this? A over C equals B over D. Is that valid? Sure, it is here. Now here we have A to C, right? So here we have the small to small ratio is going to be the same as the large to large ratio, okay? So we're not going to have to use this sort of take this theorem literally, right, to assert something, okay? We can say, right, sure, this opposite side, small to large, is equal to this smaller side to the larger side of the two when they get intersected, that ratio here. But we could also say this small segment that got cut out to the side that's adjacent to it is equal to the large segment that got cut out to the large side that is adjacent to it that didn't get intersected by the angle bisector, okay? So these get sort of presented these two ways here throughout the section and throughout problems like this here. They wrote the theorem like this. What we're going to prove it for is this situation here, but this is valid too. And we might see that in the problem set. Okay, without further ado, I'm bringing back this diagram here. I thought this diagram is kind of confusing to kind of see right away. A book only has to choose like a few diagrams for you because the book's printed out. They give it to you. So they already show their triangle in question that they'll use to prove this with. Here, DEF, right? DEF, that's a triangle. And they already have the angle bisector drawn in. And we have 3 triangles on this. This gets kind of confusing if we just started looking at this. So hopefully by my demonstration earlier, it made it a little clearer what we're trying to get out here. Here we have triangle DEF, right? DEF. DG is bisecting angle FDE, okay? So angle D in DEF. So this is angle FDE. And here we have angle 1, angle 2. What is it we're going to have to prove, okay? If a ray bisects an angle triangle, so here's all of our given premises here, right? If a ray, right, this ray DG bisects angle FDE, right, that's in that triangle right here. So we've said it all. If a ray bisects an angle of a triangle, what's the thing we're going to have to prove? Using the letters that we see here, using the information we have here, okay? What is it going to be? Well, isn't it going to be that angle, okay, sorry, that angle bisector divides the opposite sides proportionally to the two other sides, right, to the two other sides. So here, wouldn't that mean, drawing the angle bisector, wouldn't that mean FG to GE, that ratio, is the same as DF to DE? Am I right about that? Okay. Opposite side, that ratio, this to that, going to be the same as, right? We got to stay over on the left side here. I'm going this to that. So here I'm going to go this to that as well. Okay. So just remain consistent. And there we go. We got it. That's exactly what they proved for you here. Okay. GF over GE, the same as DF. There we go, over DE. And that's just something we can use here. And that's called the triangle angle bisector theorem. Remember, there was an angle bisector theorem at the beginning of the textbook that was different. It wasn't just for triangles. It was whenever you had an angle bisector. Here's this, we call this one as the triangle angle bisector theorem. And that's what we're going to prove right now. Whoever wrote this proof is pretty clever too. I got to give you this one down, credit to this one here. This is not one that I expect you guys to write on your own, but hopefully you can figure it out and show that curiosity and follow along with the logic of this one here. Let's do this right now. Let's go ahead and prove it. Okay, got our statements, got our reasons column set up. Again, 4 required parts of proof. We got a diagram drawn out, given and proved statements here. Let's go ahead and do it out here. I'm a teacher, so I'm going to go through it really quickly, but I recommend, copying it all down, marking on the diagrams, trying to figure out what is the purpose of this proof and what are some connections you can make right away. What are some things maybe you could say right away and find that pathway and work your way through something that isn't super straightforward. Step 1, like usual, is what? We have our given premises, right? We have our angle DG, ray DG is the angle bisector of angle FD. That's good, so we'll state that here. Okay, we'll probably use definition of angle bisector in a second to say that angle 2 is congruent to angle 1. That'll help us with something later in the proof. Remember, this proof is very clever. So we'll say that in a second. You might say that step 2, but I'm gonna save it because let's get to the part that I want you to visualize, okay? Why, for instance, angle 2 being congruent to angle 1, why that's gonna become important, you'll see in a second, because we're going to have to introduce some auxiliary lines. That's right. What section are we in right now? We're in section 5-6, okay, which is proportional lengths. What have we proven so far? Well, we've used the the basic proportionality theorem, okay? What is this here? We have, in the diagram here, interesting. I cut something off in the diagram here. What is this here? Was that in the other slides? I think it was. Oh, I didn't actually kick that out. It's like, why does it say parallel here? It should just say this is congruent to that. Okay, so there's a parallel in the diagram in the book. So this diagram in the book is very confusing if you were to read it here. Ignore the parallel for a second, because actually what we're going to have to do on this slide is our auxiliary set is we're going to have to introduce a line that's parallel to this one. And can you guys predict where that's going to be and why? Well, parallel line running through a triangle. We've seen that so far this chapter, right? Where have we seen where we have a triangle, right? A triangle, I'm doing a little outline of a triangle right here. Where have we seen where we have a parallel line going through? What's that theorem called? That's right, the basic proportionality theorem. So the proof of this is very neat, very cool. It's going to rely on the basic proportionality theorem. So what we're going to have to do is we're going to have to introduce some auxiliary lines to create a new triangle here. See if we can follow this one here. Draw a line parallel to DG through E. There we go. There's my parallel right there. And extend DF to intersect that line, right? Intersect that given line. And there we go. There's our diagram here now again. Wild, okay? We'll talk about the reason for a second about why you're allowed to add this line that's parallel to DG, and then why you're allowed to extend this to intersect with that parallel to DG, that line right there. But maybe we should just watch it one more time to make sure we understood where that come from here, okay? Because we started with this as the diagram here, right? Pretty neat. We started this diagram here. Remember, we're allowed to take our pen and draw certain things in as long as we have a reason for them. Okay, so maybe you think about what the reasons are, and maybe you can offer to share that with the class here in step 2. So what I can do is I can take my pen or take my constructions tool. Like ideally, right, we'd be in a classroom, be constructing things like this here. I can introduce, right, through that point E, that might help you here. Through that point E, I can introduce a line that's parallel, right, parallel to this line right here, which I just did. And then what I can do, well, let's do it back here a little bit more slowly here. This is parallel to that. And then once I've drawn that out, I can take this and then draw just a line, just extends line FT, because line FT would keep going, and I could just show it here, and then eventually it would hit point K. Okay, what are my reasons for that? I drew 2 lines, should have 2 reasons. Well, through point E, I'm allowed to draw a parallel to this line right here, because through a point outside a line, exactly one line can be drawn, okay? And once I have that drawn out, why can't I just draw from point D and just keep going with FD here and just keep drawing and eventually makes contact with a point and we'll call it K? Well, that's just because point K is there, right? Like all these are points, right? This parallel line is composed of an infinite amount of points here. So through a point here, and then when we extend it, we go through another point here. That's through 2 points, one line can be drawn. Through 2 points, there is exactly one line. There's another way that gets worded, okay? So auxiliary sets, I always remember like doing this one here too, like what is the book talking about? Like what are they talking about here? I don't remember like having a section about auxiliary sets. I did do a mini lesson last semester on that here too. So that's how we got a diagram. Okay, so we got a little distracted there because introducing auxiliary sets it's a little bit complicated, right? A little bit hard to follow, but I think you can accept we're allowed to draw a parallel there. We're allowed to extend that. If you accept that, maybe we can refocus on this proof here to figure out why we did that. What do we notice? What is this here? Well, getting back to what we've been doing recently, I always think about like, what have I proven recently? How does this get me closer? Well, I've proven something about a parallel line to a parallel line here. Notice here, FKE is a triangle. So here we have DG parallel to KE, one of the sides of a triangle. DG is parallel to one of the sides of a triangle, and it intersects the other two sides. So what do we know about that? Well, we know that it divides side FK and side FE proportionally. This is going to be our way of getting a proportion into the proof. It's not going to be this exact one, right? We're going to have to sort of manicure this a bit here to get it so something like this. But our goal here is, again, proof you're thinking about working backwards. We're trying to get that GF, okay, GF to GE is going to be the same, right? This here, remember the side of the angle bisector that got intersected by the angle bisector, right? GF to GE is equal to the ratio of the other two sides. So DF and DE, okay? And so I can get FG or GF to GE into this proof. I can get that first ratio in this proof because that is the basic proportionality theorem, right? This parallel, so here this is the angle bisector, remember at the beginning here, but it's parallel to this other parallel line that we introduced, right? We added as an auxiliary set here. So now this fits a situation where we use the basic proportionality theorem to say that, you know what? DF to DK would be in the same ratio as that GF to GE as we had here, okay? And what we notice here, what we're trying to prove, again, is this to that equals this to that. But here we have this to that. That's good, right? That's what we wanted to here. But then we have this not to that, okay? This not to that, but we have this to that we're trying to prove, right? That's what we're trying to prove here, okay? So really, we just need to get D. The only difference between what we said so far with basic proportionality theorem and what we're trying to prove is that we have a DK here, we have a DE there that we need to get towards. So the question is, how can we prove it? How can we prove it? Because we can't actually prove this. We can prove that DK is congruent to DE. What's the next connection, right? Everything's connected here, right? It may feel complex, but if you see the connections, it's not that complex. We get it here. How do we get there, okay? Well, I see here angle 3 and angle 4, they're sort of nudging us that direction. Why are they doing that? Well, this is a triangle. What kind of a triangle do we think that is? Isosceles triangle. Okay, so let's get into it here. We know that angle 1 and angle 2 are congruent because we haven't actually used this opening premise here, that's the ray DG bisects angle FDE. So let's do that right now. Let's get it out of the way. Let's get definition of angle bisector. Boom, we have it in there. Next thing, right? So if those angles are congruent, what's another thing I can say? Well, this is a parallel line. That's a parallel line. So this is angle 1 right here. That's angle 2 right there. Uh-oh, look at this. Those are congruent. What's angle 1? Hints. What else is angle 1 congruent to in this diagram? Angle 3 or angle 4? Well, angle 3, right? What type of angles are those? What's angle 2 congruent to in this diagram? Angle 4, right? Angle 4, because what are those? Those are corresponding angles. So here we have two parallel lines cut by this transversal, alternate interior angles. Two parallel lines cut by this transversal, corresponding angles. So think about that. All 4 of those angles have to be congruent, and boom, we will say that as such right here. Okay, angle 1 congruent to angle 3, because if 2 parallel lines are cut by a transversal, alternate interior angles are congruent. Angle 2 congruent to angle 4. If 2 parallel lines are cut by a transversal, corresponding angles are congruent. And then how do we know that then angle 3 and angle 4 would have to be congruent? Well, angle 3 links to 1, angle 4 links to 2, Angle 1 links to 2, right? Angle 1 links to 2. So it's a whole bunch of transitive, right? Transitive property here. They all equal each other, right? They all equal each other because they're each equal to the same thing. And that would be transitive here. Now I got angle 3 congruent to angle 4. What's the next step, okay? Again, my whole goal was, well, I got a proportion here, but I want to say these sides here are in the same proportion as the 2 remaining sides of the triangle, not this segment and then this thing down here, which wasn't part of the original triangle I cared about. Well, angle 3 to angle 4, why do you think we spend so much time proving that? Well, converse ITT. If you have 2 angles of a triangle that are congruent, then the sides opposite those angles, congruent angles, are also going to be congruent to one another. Okay, so going back there from early in chapter 3, the converse ITT, we're good to go there. And then finally, last step, did all that work? Well, we want to just replace DK here with DE, and then boom, we've gotten there. We've gotten to our not basic proportionality theorem, we've gotten to the triangle angle bisector theorem, and we're good to go. Simply just substitution. Step 6, we said dk equal DE. Remember, that was from the converse ITT. Angle 1 was congruent to angle 2. That was the given with the definition angle bisector. Between that, through our parallel lines we introduced, and then all the corresponding and alternate interior angles, angle 3 and angle 4 are congruent, so it all kind of connects together. Pretty clever proof, but we've gotten there. We've proven it, that the triangle angle bisector theorem is the thing. If we have a ray that bisects an angle of a triangle, then it divides the opposite side and a segment is proportional to the other 2 sides. Lots to take in, okay, but one thing to emphasize, this was a generic diagram here. We could have proven this with any specific triangle that we could have proven here. So I'm just going to draw another one, so maybe, well, that's not really a triangle right there. Let's get it out of the way. I'll draw another one down here just so we can see, like, you know, kind of, what if I prove it with more like a diagram that I had beforehand? So, okay, so this is obtuse here. You might be thinking it's just obtuse. Well, let's prove it with this guy right here. Well, I could have proven it the same way. If I introduced an angle bisector right here, okay, if I did that, right, and I'm trying to prove this over that, sure, I could have extended this, right? Sure, I could have extended this here. And I could have introduced a parallel to this line through this, okay, right? If I introduce a parallel here to here, right, parallel, okay, check it out here. If I had this A, B, okay, and this is C, D, okay, and my goal was I'm going to show A over B equals C over D. This would work the same exact way that I just kind of proved this one here. This is parallel, so this is congruent to that, so let me do that here. This is an alternate interior angle, right, with parallel lines. So all 4 of these angles are congruent. Okay, I just drew like a random triangle to show you this can work out with other things here. So now I would know that B to A, right, would equal D to F over here or something like that, right? F over here, okay? But hey, look at this. F and C got to be the same thing because here we have 2 angles congruent, converse ITT. Okay, so just wanted to show this to you. This goes for any triangle, not just the one that we kind of proven out here, okay? So I don't know if you really followed that, if that was really worth it, but I have it up there anyways. Okay, next thing up here, your brain's probably melting. Brain's probably melting a bit here, but I have some practice problems for you guys. So let's go ahead and jump into it. State a proportion for each diagram. Here we have the triangle angle bisector, right? Sorry, not the triangle bisector. It's going to be the triangle and bisector theorem you're going to use here. But here we have an angle bisector of a triangle. How does it divide that opposite side? We're talking about that opposite side. What can we say about the ratio of n to g? It's equal to what? Continue on with this one here. A little bit more algebra on this one. Ooh, this is the corollary of the corollary of the basic proportionality theorem as number 5. So I included that one in there for whatever reason. And then a little bit more challenging. This is number 25. I think, on the homework that you'll have Tuesday. So a little bit harder of a problem here, okay? So with that, take it away. I'll give you 2 minutes to work through this one. 2 minutes, okay? Ready, set. It's on now. You better believe it. It's on now. Minute done. Come on, come on, come on. How are things coming along? Go, 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 go. Got this. Feel the proportions. I have faith in you. You can do it. 25 seconds. Seconds. 4, 3, 2, and 1. So let's go through this together and check your answers, or maybe you didn't do it, you'll just do it along with me, but hopefully you gave it a shot here, okay? Angle bisector, okay, angle bisector here, we got that over here. So we know that about this opposite side of the original, right, the original triangle here, that this got divided proportionally to the other two sides. So that's just simply n to g equals a to b. There we go. We got that one knocked out here. I could have also said a valid proportion that you could have said for this one here too. Check it out with a mean swap here. I just want you to notice this here, that n to a, okay, if I mean swap here, the smaller segment that got created to the smaller side of the triangle is going to be equal to the larger segment that got created on the third side, to the larger of the two sides of the original triangle here. So that would be G over B. Okay, that could be verified through a property of proportions. Here's the literal translation of the triangle angle bisector theorem. Okay, N to G equals A to B, but N to A, right, if we want to take it this way, N to A equals G to B, perfectly valid too. Okay, so that's sort of how you'll see another way of those proportions being represented here. Okay, so let's check this one out. Maybe we'll set up, we basically choose from either of these two. Doesn't say solve it, but maybe we can solve it together here. Stated proportion for each diagram, number 4. Okay, opposite. So this would be 10 minus x over x equals 9 over 6. There we go. Simple as that. Solving this one, cross multiplication. What I would, I guess I wouldn't have changed this up the way I would set this proportion. I would just solve through cross multiplication. So anyways, 6 times 10 minus x, that's 60 minus 6x. And that's going to equal 9x. You don't have to do this here, but it just like takes 2 seconds. Might as well do it. Another example here. 60 equals, add 6x to both sides, you get 15x, and x equals 4. All right, kinds of stuff you'll have coming up on your exit ticket and your problem sets later today and tomorrow. Okay, this one here, this is just a review. You might have had this on homework already here. This is in a 3-to-2 ratio. Okay, check it out here. This is in a 3-to-2 ratio. This is the corollary of the basic proportionality theorem, but it's in a 3-to-2 ratio over here, and that means that this is going to have to be in 3-to-2 ratio, y over 14, okay? And 2y equals 42, so y equals 21. And it makes sense, right? That's 1.5 times higher than this. That's 1.5 times higher than that. We're good to go. All right, number 25 here. Let's check this one out here. Well, they gave us the numbers here, so sketch it out on your problem sets. A lot of people draw diagrams. I think that really helps here. So AC is 60. Well, that's tricky. CD is 30. Okay, hopefully you're watching this one, actually. A lot of people would have trouble with a problem like this. Watch number 25, yes. Okay, CD is 30, AD is 50, okay? AC is 60, so the BC, what the heck is that gonna be? Ooh, we gotta figure out a way to solve this one. Ooh, it's tricky. Your key to solving a problem like this, okay? Listen up if you struggle with this one, because I imagine a lot of people did. Your key to solving a problem like this is actually number 4 above here. Okay, number 4 above here. How do they set this up? Well, this is 10 minus x here. That's x. Why? Because this side here, it's as if they had given this side to you as side length of 10. Okay, side length of 10 here. So picture, this is pretty much identical to this problem down below here, right? Number 4 is pretty much identical to this, except they've set up their expressions for the 2 unknown sides here, okay? 2 unknown segments, right, that we might need to find, right? We need to find BC, we could find AB too, we can figure that out. There has to be BC in this question. Okay, why? Because we didn't know the segment length, we didn't know that segment length, but hey, this is actually 10, right? Because 10 minus x plus x, right? Minus x and plus x will cancel out. That means this side here is 10, okay? So this is very similar here. So look at number 4, doing number 25 is basically following the map, right? The map that they put out for you on number 4 here. And that is, if AC is 60 right here, we basically need to create expressions for what's unknown. So we'll let BC equaling length x, okay? So if this distance here is x, okay? This whole distance here is 60. Question, what's the expression I can set up here that would, using segmentation postulate, what plus x equals 60? Well, it would be 60 minus x, okay? BC equals 60 minus x, and AB equals 60 minus x, and BC equals x. And now we just need to solve it the way we did, like we did on number 4 here. So what we have to solve this one is going to be set up a proportion. That was the direction here for each diagram. So we're like, what? I don't know what AB is. I don't know what BC is. You're going to set it up using an expression like this here. So you'll have 60 minus x over 50 would equal x over 30. Okay, x over 30. You could have also realized, too, that this would have been in a 3 to 5 ratio, right? 3 to 5 ratio right here. Okay, so you could have actually made this 3x and that 5x. X would be, ooh, I need a decimal here. Anyways, I might be working too far ahead of myself here. But we get this. Let's go ahead and solve it, right? Might as well solve number 25 because this is a harder problem, I think, on the homework tomorrow. But 50 times by x is 50x, right? We would cross multiply 50x. And then 30 times by 60 is what? 1800? Oh, we're getting big here. We're getting big here. 3 times 60 is 18. We got 2 zeros, tack on 2 zeros there. So we get 1800 minus 30x. Okay, so 80x would equal 1800. I think we need a calculator for that because I don't think 80 goes into 1800. So let's go ahead and I'll pull out my calculator. And to solve this here, we're going to do what I got, 1800 divided by 80. Oops, not 82. And I get 22.5. Okay, BC, I got 22.5. There you go. Okay, there you go for that one. All right, that was all your examples. That's all you get. That's all you get for free there. So now it's time to do some exit ticket problems. Again, you'll get feedback on those. We will do the problem set on Tuesday. You'll have a Jamboard review on Wednesday and begin studying for your Chapter 5 quiz. Are you coming to office hours? Are you going to lose low CSF tutoring, or are you seeking out help? Okay, so what I'm seeing has been good enough, but I know that there are some people who could improve. Okay, so figure out, right? Think about ways that you can improve if you're looking to improve here. Okay, so there are special situations where segments are divided proportionally. That is section 5.6 in a nutshell. Right, so remember, this is basically our third kind of lesson. We had that mini lesson on Friday, third lesson with section 5.6. We had 3 scenarios where segments got divided proportionally. First of all, what is this one? This one's the basic proportionality theorem. That's right here. So in this one here, let's maybe come up with the proportion here. Well, this would be 9. So, right, if we wrote a ratio for this one or a proportion for this one, I'm going to change colors too. Okay, this would be, my proportion I can set up here. I can set up many proportions in this one here, but one that I might be interested in setting up is 9 to 6. Would be the same as, well, this would be 20 minus x here. Okay, so it would be x over 20 minus x. There we go. That's a proportion I could set up. I could solve for x in that one. I have enough confidence to do that. Hopefully you do too. Okay, that's basic proportionality theorem. When we have a parallel line to one side of a triangle and it intersects the other 2 sides, it will divide those other 2 sides proportionally, right? This to that, right? X over 20 minus x equals this to that, 9 over 6. And we'd be able to solve that. We'd be able to determine an unknown on this one here. Here, this is the corollary, right? Followed very quickly from the basic proportionality theorem, where if you have 3 parallel lines and they're intersecting 2 transversals, right? They would. They're just showing us 2 transversal here. That 12 to 6 would be the same as 7 to, this would be 14, right? You can do some of them in your head if it's like easy. This is twice as large here. This is going to be twice as large here. 6 over 12 equals 7 over x. Cross multiply solve, you get the same thing. You get 14 there. And then finally, last one, that's the one that we did today, which is we start with a triangle here. Again, right? We're just starting with a triangle. We don't start with 3 triangles here. We have an angle bisector here. This here, 9 to 5 would equal this large side over that small. So this larger segment that gets created to this smaller segment that gets created. Same ratio as the remaining 2 sides of the triangle, 12 over x. We'll be able to solve for x here. What, 9x equals 60. 9 doesn't go immediately into 60, so we're going to our calculator. To move efficiently here, 60 divided by 9 is 6 2/3. Okay, so x would equal 6 2/3. So that might be a question that potentially that's on your homework tonight on that one there. Okay. Basic proportionality theorem, correlated to basic proportionality theorem, and triangle angle bisector theorem. Again, just ways that we can see situations that come up where segments get divided proportionally. And there you have it. Section 5.6 all done, and we're done with chapter 5. Yes, we are done, my friends. We are done here. Yes. Okay, so I've already shown, I did this during a lesson last week during our Desmos thing here. I've already kind of shown you here, right? We're at the point now, right? You start thinking about this quiz that we have on Friday. thinking about maybe reviewing some of this stuff here. So again, whatever's a ratio. What's a proportion? Okay, what are the properties of proportions? Mean swap, a denominator add, invert the fraction. What else? Oh, means extremes property, right? Cross multiplication. So you should be feeling pretty confident about those, about how you can manipulate proportions, okay? Similar fingers have the same shape, right? Two polygons are similar if and only if corresponding angles are congruent and their sides are in proportion, okay? Same shape, different size. Well, maybe different size. Maybe they're congruent too, because congruent figures are also similar to one another. Ways to prove two triangles similar. We got the AA postulate, SAS similarity theorem, and SSS similarity theorem. That's right. We proved the latter two. And then finally, we've had since Wednesday's lesson, right? This is our basically third lesson. That was Thursday's lesson. We've had ways to show that segments are proportional, okay? This was actually before that, right? Corresponding of similar polygons, they're in proportion, right? They're proportional, okay? So if I just have similar polygons, this to that, and then the corresponding sides also need this to that, okay? The thing we got in 5-6 were these three scenarios that I just reviewed to you here. So make sure you brush up on that, review that, and yeah, we made it. Exit ticket today, problem set tomorrow. I know you have a decent amount of work. But then, right, you start reflecting, going through your notes, going through old exit tickets and old problem sets, because really your homework is your study. Email me if you have any questions. Thanks so much, guys. Take care. Have a great one.